begin with exploring the history of topographical maps, but before we get there, a topographic map is a type of map characterized by large-scale detail and quantitative representation of terrain, usually using contour lines. By exploring a comprehensive timeline of the map's history, we gain a thorough understanding of how the maps developed into what they are today. In the late 1700s, the first multi-sheet topographic map series of the entire country was complete. Topographic maps have many of the same features you will find on any maps you may be more familiar with. For example, they have a legend, which is a visual or written explanation of symbols used on the map. There's also a scale, which refers to the ratio between the distance on a map and the corresponding distance on the ground. There's also coordinates, which is a system used in geography that enables every location on Earth to be specified by a set of numbers, letters, or symbols. Moving into the early 1800s, the Great Trigonometrical Survey began in 1802 and was a project which aimed to measure the entire Indian subcontinent with scientific precision. This project led into the late 1800s. At this point, topographic maps were being used in many different ways, even by the military to assist in planning for battles. As they continued to evolve, topographic map series became a national resource in modern nations for planning infrastructures and resource exploitation. Now on to the early 1900s. 1913 saw the beginning of the International Map of the World initiative, which set out to map all of Earth's significant land areas at a scale of 1 to 1 million. Although the project eventually fell apart, it left an indexing system that remains in use to this day. By the 1980s, centralized printing of standardized topographic maps began to be suppressed by databases of coordinates that could be used on computers. For example, the federal government and the United States Tiger Initiative compiled many interlinked databases to support locating street addresses within street segments. Digital elevation models known as DIM were also compiled, initially from topographic maps and stereographic interpretation of aerial photographs, and then from satellite photography and radar data. Going into the 1990s, Tiger and DIM datasets greatly facilitated geographic information systems and made global positioning systems much more useful. Now today, topographic maps are prepared using photogrammetric interpretation of aerial photography, LiDAR. As we go further into this more digital era, the future of standardized digitally printed topographical maps is less somewhat in doubt.
Scientists have been noticing a growing problem in our dependency on GPS. They affect our natural ability to navigate, meaning we can't project mental maps or internal pictures of the world. This gives us poor spatial memory and the inability to make spontaneous and flexible decisions in our environment. This means there's a value on physical maps. They help orient ourselves in the world. We can pay attention to our surroundings, assemble pictures in our head, and figure out how to get where we want to go. It also allows a sense of adventure. You can deviate from your route or improvise when the situation calls for it. However, maps give a distorted view of the world. Mercator's projection was created in 1569. It was a useful tool for navigation. The lines for longitude and latitude helped guide ships at sea. In Mercator's projection, the shape and size of continents increase further away from the equator. Greenland appears roughly the same size as Africa. Alaska looks almost as large as the continental US. Europe, excluding Russia, seems only a bit larger than South America. And Antarctica dwarfs all other continents. Gall-Peters projection, in comparison, resolves many sizing issues. Africa is actually 14 times larger than Greenland. Alaska fits into the US multiple times. Europe is much smaller than South America, and Antarctica is the third smallest continent. This gives us a potential solution. Gall-Peters gives an equal area projection, meaning regions are preserved more accurately. It comes closer to showing how the southern hemisphere is 2 times larger than the northern hemisphere. Proving Mercator's projection gives a Eurocentric bias that can harm the perception of developing countries. But this is not a perfect solution. While Gall-Peters doesn't disproportionately enlarge areas, there is stretching horizontally near the poles and equator. No mapping projection system can show the world accurately. Each projection has its own advantages and disadvantages.
So now that we know a little bit about the history and background of topographic maps and the controversy over maps in general, let's get practical. How do we use a topographic or topo map? First, let's take a look at this one here. In every map, there are always symbols and line colors which represent features of the terrain. The reliefs or elevation changes are commonly found in brown or pink. We'll get back to these more in a minute. Hydrography can include anything from lakes and rivers to waterfalls. Vegetation is typically green and refers to any wooded, rush, or grass-like features of the terrain. It is common that the darker green areas represent a greater density of vegetation and lighter shades of green represent sparser vegetation. Roads, trails, and manners of transportation are typically found in red. Any man-made or man-defined features such as buildings, Political or geographic boundaries, or names of places, are typically found in black. However, each map is different, and so it's important to check the legend to ensure that you understand your map correctly. This is also where you'll find what each of the various symbols peppered across your map mean. A minute ago we mentioned being able to determine the contours of a terrain based on the curvy brown or pink lines we see on a map. As it turns out, these lines are called contour lines. Each line represents a certain elevation, so anywhere along that line, the terrain will be uniformly at that same height. Pretty nifty, right? What this means is that we can determine how steep or flat the terrain is in a certain area. If the lines are closer together, it means the terrain is steeper. If the lines are farther spread out, it means the terrain is more gradual. Usually every 5 or 10 lines, there is a bolded contour line that shows the elevation at that location. This is called the index line. On every map, there is a given contour interval. This can be anywhere from a few feet or meters on maps with steeper terrain to hundreds of feet or meters on maps showing flatter terrain. The legend of a map will always have the contour interval listed. This image shows an 80-foot increase at each contour line.
Compasses are extremely crucial because although GPS is now widely available, signal can often fail in the midst of rugged terrain. It is also useful when you don't necessarily need to know the actual direction, but are heading towards a certain feature that is visible from your start point, but may not be visible throughout the hike due to vegetation or other issues. The most common compass has a base plate, a movable bezel, a north needle that's usually red, and a direction of travel arrow. The front of the compass is the end without the cord attached and has the direction of travel arrow on the base plate. The red part of the needle is always pointing towards the Earth's magnetic pole. If you want to go in a direction that is not north, you use the compass housing, which has a scale of 0 to 360 or 0 to 400 degrees. The compass should have the letters N, S, W, E for north, south, west, and east. It is useful for navigating without a map, however it takes training and experience to properly learn. The first step for using a compass is to align the edge of the compass with the starting and finishing point. Rotate the compass until the orienting arrow and lines point north on the map. Rotate the map and compass together until the red end of the compass needle points north. Follow the direction of travel arrow on the compass, keeping the needle aligned with the orienting arrow on the housing. Align the orienting lines and the orienting arrow with the meridian lines on the map. When navigating, hold the compass in your hand with the needle well aligned with the orienting arrow. Then finally aim in the direction of travel the arrow is pointing. To return to the starting location, rotate the compass bezel 180 degrees. However, you have to be extremely cautious that the red part of the arrow points at north in the compass housing. Local magnetic attractions might be a potential problem. Carrying something as small as iron can disturb the magnetic attractions, and there is a possibility of magnetic attractions in soil as well, but it is rarely seen unless you are in a mining district. You should not stare at the compass when navigating. Instead, aim at some point in the distance and go there. You cannot always expect to get to exactly what you are looking for. How much you get off course depends on the environment, such as visibility, forest density, and personal experience.
So now you know how to use a compass. But what can it tell you? Well, one of the most important things it can tell you is your bearing, or the direction towards which you're headed as shown specifically by your compass, when we refer to it in the navigational sense. There are two types of bearings, relative and absolute. Relative bearings are calculated based on local landmarks and calibrating your compass to them. The second type of bearing is an absolute bearing. This is based off of true north. Absolute bearings are particularly useful when you're trying to orient yourself based off of a map. If you're using a compass and a map, it's important to make sure that you've calibrated your compass to your map. In order to do so, you need to use the declination as the legend or in the bottom of your map. The important portion of the declination in this image is the degrees between true north and magnetic north. This tells you how much you have to turn the bevel on your compass to the right or the left in order to calibrate your compass. What is that, you ask? Well, if you take a look at this example, the center arrow is to true north. True north is an absolute value and what we would consider north traditionally to be. It points towards the North Pole. Magnetic north, however, is a location-specific relative north. Each map gives you exactly how far off your magnetic north will be from your true north based on the local magnetic fields. Grid north is the arrow to the right. Grid north indicates if your map is not pointing in the true north direction. For example, our arrow is pointing slightly to the northeast, meaning the map would appear to be facing north, but is actually facing a northeasterly direction relative to the rest of the world. One of the most important features of a map is the scale. The scale allows you to use a topographic map functionally. It allows you to be able to measure the distance between two locations on a map with a ruler, piece of string, or even a hair tie. This woman is demonstrating how to use a piece of string to measure the scale bar and trace this on a map in order to measure the distance from her current location to where she'd like to end up at the end of the day. The scale bar allows you to use objects other than a ruler to measure the distance. The scale of 1 to 50,000 represents the ratio of 1 centimeter on the map to 500 meters on the ground. This ratio is calculated based on the map's distance over the ground distance. However, it's usually listed for you right below this scale. It's also possible to deterministically measure your coordinates on a map. This is an example of the grid you would find on a map. It shows how the coordinates are laid out and how it's possible to find your absolute position on the map with a straight edge of some type. This is important in case you need to give out your location to someone. When determining the coordinates, you read a map from the left to the right or so that the numbers are increasing. In this example, you would say your easting is 499400 meters due east, and your northing is 5453000 meters due north, near Mount Stewart.